Welcome, everybody. We'll get started in just a few seconds. Okay, and I do have 1:30 Eastern, 10:30 Pacific, so let's begin. Hello, everyone, and welcome to today's AEESP webinar supported by Sustaining Member OLI Systems, Advanced Thermodynamic Approaches for Mitigating Environmental Challenges Leveraging OLI's Simulation Technology. I know that we are all eager to get started with today's presentation, but just a couple of quick housekeeping items before we do. We'll be taking all questions today at the end of the webinar. That being said, please feel free to ask your questions at any time during the session using the Q&A section located in the bottom toolbar, like is shown on this slide. Another reminder that you all will receive the webinar recording and slide deck after today's session. So thank you again to AEESP Sustaining Member OLI Systems. And without further ado, I will hand things over to our moderator, AEESP President, Cara Nelson. Cara, please take it away.
Thank you so much, Erica. I want to begin by welcoming everyone. So it is my great honor to serve as the president of the Association of Environmental Engineering and Science Professors. I myself am a professor at UC Berkeley in the Department of Civil and Environmental Engineering. This is our second Sustaining Member webinar, and these webinars are a new program that we believe will be of great benefit to our members and the broader community. They are free to attend, and you do not have to be an AEESP member. If you are not familiar with AEESP, we are a diverse and inclusive community of over 1,400 members, which includes educators, researchers, and graduate students. OLI Systems is what we call one of our sustaining members, and this is a special category that we have for companies and organizations. I want to emphasize that AEESP is an organization run by volunteers, and we have a wide range of activities and programs that support the professional development of our members and that aim to evolve our field to address the grand challenges of today and the future. So if you would like to learn more, if you're not that familiar with us, please go to our website. It's aeesp.org. You can also look for our activity on LinkedIn. You could also send me an email, which I will put in the chat once we get started. And you can also find out how to contact me on the website. And if you are not already a member, I hope you will consider joining. So now let me introduce our speakers today. Vineet Ram leads the incubation and development of new research and business opportunities related to sustainability applications and emerging markets at OLI Systems, and he holds advanced degrees in both engineering and business. And Dr. Gaurav Das is principal chemical engineer in OLI's database and research team with a focus on modeling and parameterization of electrolyte systems. And Dr. Das received his PhD in chemical engineering from Vanderbilt University and his bachelor's in chemical engineering from Jadavpur University. So with that, I will turn things over to our speakers.
Great. Thank you very much, Cara. First off, I would like to thank Cara and the AESP leadership team for this opportunity to come in front of you. I'm going to give you a quick introduction to OLI, so you know a little bit of what we do, and then turn it over to Gaurav for the main technical presentation. Next slide, please. Can you advance the slide, Gaurav? No. Great. So essentially, OLI is really an expert in understanding water chemistry behavior and translating that into very predictive software that can translate into very, very specific software applications across a broad range of industries. The real element here is water chemistry and electrolyte behavior impacts how we think about designing processes, how we operate them, and really looking at the outcomes around reliability, efficiency, optimization, or sustainability. All of these outcomes are impacted by a deep understanding of electrolyte and water chemistry behavior. And that's really what OLI does across and applies it across a wide range of process industries. Next slide, please. OLI is a 52-year-old company. We have very deep expertise in electrolyte and water chemistry-based solutions for process modeling and simulation. We have a very comprehensive software platform with very rigorous ability to understand chemistry with a comprehensive database and a software portfolio. In addition to that, we've been doing tremendous research and development innovation for over 3 decades in strong partnership with academia, national labs, universities, and government organizations. We have deep expertise in translating a lot of these with scientists like Gaurav who are responsible for thermodynamic and kinetic modeling. We also have application engineers and solution architects who deliver real world solutions to our customers. And finally, we are a global organization with presence in over 35 countries, 6 continents. We have about 500 clients, and we really are looking to expand our engagement with the AEESP community going forward. Next slide, please. Very quick view. Sustainability in essence is sort of what we do at OLI. We have been thinking about asset performance and environmental quality for a long time, for many decades now, and our solutions have been enhancing them, and we've been rapidly shifting to decarbonization and energy transition, and we've been looking at a number of things in that area as well. So really, when we think of engaging with this community, it's so close to us because we have been thinking a lot about environmental science and engineering for many decades right now and trying to solve real world problems in this area. Next slide, please. This is the heart of our collaboration. This is what has given us the ability to develop industry-leading solutions that are deep in chemistry understanding and thermodynamic modeling. This represents our partnership across the ecosystem, everything from the US Department of Energy to various national labs to a whole range of entities. You can see here leading academic institutions across a broad range of areas, whether it be things like corrosion or geothermal energy or battery recycling. We've been at it for a long time, and we're really hoping to expand that partnership now with through SERDIP program, with ESTCP and academic colleagues like yourself in areas like PFAS as we go forward. Next slide, please. We do have a comprehensive software portfolio. OLI, at the end of the day, is a software company. Majority of our revenue is through enterprise software applications. We have it available on the desktop. We have cloud-based products. We provide service, support, training, and education. And we'll be happy to talk to you about some of this as well. And we have today clients licensing our software across a broad range of industries, from oil and gas, chemicals, mining, battery recycling, lithium extraction, water treatment, etc. Next slide, please. Our experience spans what we would call TRL stages across the board, and we think of it as asset lifecycle, everything from basic R&D and doing lab scale proof of concepts of lab scale pilots all the way to proof of concepts, demonstration facilities to full-fledged operations. Our technology really applies across the board. We started with research, but today we apply it across the board. So no matter the TRL stage of your research, we can engage and support support that through our solution technology. Next slide, please. In terms of enterprise software, we do have different ways we package and license our software for commercial customers and for industry-funded research projects. It's typically an annual fee that varies based on number of users, type of size of the organization, the term of the contract. We do work on a case-by-case basis for academic research projects as well, just based on strategic alignment of the topic. And we do have classroom and teaching licenses as well, which help, and we do a number of senior project type of support for classroom for licensing for our software. We'll certainly be happy to talk to you more about it as you see a need. Next slide, please. And really, this is my final slide. We're really seeking active collaboration on research program with this community. There's a number of areas we've been sort of looking at. Probably foremost in our mind is around toxic contaminants and PFAS in particular. OLI is a leader in modeling, simulation modeling. We like to partner with those who have deep experimental capabilities so we can come together to develop the right kind of first principles-based models for areas like PFAS, which don't quite exist today. So this would be a great way to kind of bring that our proven technology and solutions to help solve real-world problems in PFAS remediation. With that, yeah, turn it over to you, Gaurav. Thank you.
Thanks, Vineet, and thanks, Kara, for giving me the opportunity to present over here. And with that, good afternoon, everyone. Today, I'll be talking about advanced thermodynamic approaches for mitigating environmental challenges, leveraging OLI simulation technology. My name is Gaurav Das. I'm Principal Chemical Engineer with OLI Systems. So here is a brief background of my today's talk. Every chemical process leaves a environmental footprint, be it as a trail of chemical compounds or byproducts. That has impacts which are multifaceted. Persistence and bioaccumulation of these compounds poses significant risk towards biodiversity, water quality, and food security. Even it threatens heart trophic levels and increases the health risks such as acute poisoning, cancer, and neurological disorders. Hence, understanding the complexities of the interaction between these compounds and environment is essential for devising novel solutions. And thermodynamics could play a great role over here because thermodynamics could simulate and predict behavior of these chemical compounds, such as how they dissolve, react, or transform into other products to track the fate of contaminants. So in my today's talk, I'll show how to use thermodynamic modeling in order to garner understanding on the toxic pollutant, starting from heavy metals to the persistent organic compounds such as PFAS. Here is the outline of my today's talk. First, I'll give a very brief overview on the thermodynamic foundation, the specification-based mixed solvent electrolyte MSE model, and then I'll go into specific examples where I'll show applications of the MSE model for solving the problems related to rare earth elements and its impacts into microbial system, mercury, understanding the chemistry of it, which has an impact on the nuclear waste. And at the end, I'll talk a little bit on the PFAS and how thermodynamic modeling would end up identifying the remedial actions of this emerging contaminant. And at the end, I'll conclude with some key highlights. In the mixed solvent electrolyte model, or MSE model, is a speciation-based thermodynamic framework. The MSE model was developed considering all the solution-based phenomena: acid-base reaction, complexation reaction, redox reaction. Some solid phase may precipitate out of the solution. So we do consider precipitation reactions. Also, surface complexation and adsorption phenomena is included as needed. So MSE model has been developed by considering several building blocks. Standard state properties of solution pieces, which includes ion and neutral species, considers ion or neutral species in an infinite dilute solution, where the excess gives free energy model, which is the heart of this framework, brings those ions from infinite dilute solution to the finite dilute limit. The gas phase is modeled using the equation of state, SRK, whereas the standard thermochemical properties are being used for modeling solid phases. Also, as needed, we could include the adsorption model. And in all together, we solve for phase and chemical equilibrium. The input goes into the transport property model. Also, our process simulation, corrosion simulation, or oil spill scaling and inhibition phenomena. The heart of this model lies in accurately representing the aqueous chemical potential of the species, which has two parts, which one comes from the standard state property, which is obtained from the HKF equation of state, and another is non-ideal part, which gets computed from the excess Gibbs free energy model. Now the excess Gibbs free energy model has three parts, which is the long range, representing the electrostatic interaction between the ionic species, which is represented by Pizarro-Debye-Heckel equation, and the local composition model, which is basically unicoque, representing the dispersive interaction between the neutral species, and the mid-range ion and ion neutral molecule interactions, which is represented virial type equation, the parameters of which are obtained by fitting to the experimental phase behavior and thermodynamic property data. Now, I have utilized this framework to study some of the complex systems maybe responsible for ecological problems. I'll start with rare earth elements. Ubiquitous presence of rare earth elements in renewable energy technologies and also modern electronics and electrical devices had increased the environmental fluxes of these compounds coming from mining, processing, and product disposal. Changes in rare earth concentrations in the wastewater stream could affect the microbial ecosystems responsible for pollutant degradation and nutrient recycling. While the impacts of rare earth in the on the microorganism in the anaerobic conditions are well studied and reported, the effect of those under anaerobic conditions are yet to be fully established. In this regard, this research has been conducted, especially investigating the effects of europium and samarium, two adjacent rare earth, with different concentration ranging from very low, less than a micromolar to 600 micromolar on anaerobic fermenters bacteria. The impact, what we investigated, that whether the bioavailability of some of these rare earth elements could adversely affect this anaerobic bacterial function, such as their cellular growth or metabolism. Within the anaerobic conditions, it's a highly reducing condition, and redox potential play a role in changing the redox states of some of the elements. As the first step, in order to solve this problem, the key subsystems has been identified and thermodynamically modeled. And I present the results for rare earth hydroxide. Here I present for europium and samarium hydroxide, which are key subsystems. Rare earth hydroxide could precipitate in two forms, either amorphous or crystalline. Amorphous solubility is an order of 4 orders of magnitude higher than the crystalline, and the transition from amorphous to crystalline is a kinetic-driven phenomena and happens over time. Experimental data are available for both of those solid phases, but rather scattered. So MSE model has been utilized to model this experimental data over the range of pH and temperature, which provides a good qualitative representation, if not the quantitative one. The solid phase has been characterized through the assumption of difference Gibbs free energy, standard state Gibbs free energy, and the effect and the solubility of this rare earth hydroxide is driven by speciation phenomena. So specific species has been incorporated in the model, such as rare earth 3+, OH 2+, rare earth OH2, and neutral OH3 species. Since there are no data available for europium 2+ and samarium 2+ system in terms of solubility, so standard state thermochemical properties have been used to represent those systems. Once all the subsystems are being modeled, we have conducted the thermodynamic simulations for the entire systems. So rare earth elements in the PYG medium, which constitute of calcium, magnesiums, potassiums, other cations, along with phosphate, sulfate, carbonate cations. So here are the simulation results represented in terms of Pourbaix diagram. So this is the pH versus potential diagrams, which actually illustrate the stability regions for different solution species along with precipitating solid phases. So what this represents that at lower pH within the water stability region denoted by this dotted line, samarium 3+ is the stable one, and the higher pH, samarium hydroxide 3, which is the neutral species, is the stable one for the initial samarium concentration of 0.6 micromolar in the system. Samarium 2+ is unlikely to dominate or form, since its stability region lies outside the water stability region in this diagram. Now, over time, since amorphous samarium hydroxide doesn't precipitate, the solubility of samarium hydroxide crystalline is higher, so it precipitates over time. And this has been captured also by aqueous speciation and solid precipitation diagram. What you can see with the variation of pH, samarium 3+ ion is dominant in the solution phase. However, as the pH increases at the higher pH, samarium 3+ actually gets into the solid phase as it precipitates as samarium hydroxide 3 crystalline phase. Also, the precipitation of this samarium hydroxide also dependent upon the initial samarium concentration in the inflow. As you can see, as we increase the amounts of samarium in the solution from 0.6 micromolar to 60 micromolar, you can see the precipitation of samarium hydroxide in the amorphous phase itself as represented by the solid green line. One thing important to note in all these simulations, whether aerobic or anaerobic, there is no appearance of samarium 2+ ion in the aqueous phase, but it changes as we shift the system from samarium to europium. So in the Pourbaix diagram of europium at the low pH, europium 3+ is the dominating solution species, as we did see for samarium. However, for a brief pH region, samarium 2+ actually becomes stable and falls within the water stability region. And the higher pH, samarium hydroxide 3 aqueous species is the stable with samarium hydroxide crystalline phase precipitates. And that is reflected on the aqueous speciation and the solid speciation diagram. As you can see in the non-environment, in the solution phase, europium 3+ is the stable aqueous species, while europium OH3 solid precipitates at higher pH, starting at pH 7. But it changes in the reducing environment, which has been simulated with the incorporation of hydrogen. Actually, you can see the appearance of europium 2+ ion. And that actually increases the bioavailability of the europium, beyond the region in the northern environment. Now, europium 2+ is available till pH 9. So this could affect the microbial functioning. And here I represent the summary of our study. Actually, which tell when shifting the rare earth elements for samarium to europium, there is a greater propensity that europium will be bioavailable for the wider range of processing conditions vis-a-vis pH. So thermodynamics MSc framework enables investigation of experimental data with predictive simulation to garner insights. As this data has been utilized for the understanding of the functioning of microbial system, which indeed show under the presence of europium beyond 60 micromolar of concentration, this indeed affects the microbial functioning. And this insight has been gained through EPH and solubility stability diagrams, which provides insight on rare earth transformation between, especially for europium, between 3+ oxidation state to the 2+ oxidation state. With this, now I'm switching gears, going from rare earth elements to the mercury chemistry. Mercury is one of the most chemically complex and hazardous element, as it could exist in different oxidation states. It could exist as a liquid metal, mercury 0 valence, or in the terms of mercury 1, mercurous and mercuric, in terms of inorganic salts and also organomercury compounds. It's prevalent, although in a trace amount, in the nuclear waste. What I can show here is the picture of hand-poured nuclear waste storage tanks where these mercuries are being found in the form of dimethyl, methyl, mercury chloride, and hydroxide under anaerobic conditions under the effects of microorganism. Also, mercury is prevalent in other industrial processes such as coal combustion, metal smelting, core alkali, and flue gas desulfurization. In order to devise a remediation action, which is critical for safety and regularity compliance, we need to model separation processes. And thus, understanding of the thermodynamics properties, such as partitioning across different phases, vapor, aqueous, vapor, liquid, which solid phase will precipitate. So the stability or metastability of different solid phases concerning mercury and their volatility and complexation, this thermodynamic behavior are of utmost importance. So with that, now I am presenting some of the interesting result. These are organomercuric compounds. Dimethyl ethyl has a huge volatility, and volatility is given by the vapor pressure. For dimethyl mercury, there are a lot of experimental data is available as a function of temperature, which shows the increase of vapor pressure with the temperature, and MSc model does a good job in representing the existing experimental data. However, for the mixed system, a mixture between dimethyl mercury and water, not so many data is available. Most of the data, few data points are available within the water-rich phase. So we have now predicted and constructed this VLLE diagram ranging across different composition of water and dimethyl mercury, which are very important for devising LLE or VLE separation processes of these compounds. Apart from dimethyl mercury, there are also indications that within this nuclear waste storage, there are other compounds such as methyl mercury chloride may be present. And methyl mercury chloride shows sublimation, which is the vapor solid transition. There are some sublimation data exist for methyl marker chloride has been modeled using experimental data, where the model has been able to predict beyond the availability of the experimental data, which is mostly available around room temperature. And also this model parameters has been utilized for predicting or estimating the dissociation constant for methyl marker chloride, which actually in the aqueous phase present of the salt, such as sodium perchlorate, is dissociates into the methyl mercury and the chloride ion. And this kind of partitioning or speciation phenomena is very important, which drives the solubility of this compound in aqueous phase. There is other compounds of interest, which is the methyl mercury hydroxide, which precipitates as the pH goes high. There are only few experimental data points are available. However, this system is very important in terms of speciation. In order to model the system, there are various species are being considered, which is methyl mercury hydroxide aqueous species, methyl mercury +1, and dimethyl mercury hydroxide +1 species. As a function of pH, the solubility of methyl mercury hydroxide are being well captured. Also, we can predict the speciation phenomena at low pH, where the solubility is very high, is driven by the solubility of the methyl mercury +1 ion, where the dominating species in the intermediate pH, it transitions into dimethyl mercury hydroxide +1 species. However, at a higher pH, beyond neutral 7, the dominating aqueous species is methyl mercury hydroxide neutral species, where most of the methyl mercury precipitates as hydroxide. Also, there is an interesting phenomenon when some organic complexant is present, such as oxalate. So mercury can interact with and form solid phases, which have different oxidation state. For example, the interactions of mercury with oxalic acid. Mercury can precipitate in the form of mercurous oxalate, which is dihydrate, which shows the lower solubility. Also in the form of mercuric oxalate, which shows the higher solubility, and the temperature, which has been represented all with the MSE model, and the temperature trend has been preserved. While for this oxalate system, the solubility of the mercuric is higher than the mercurous system, this trend is not evident with all the organic complexant. For example, glycolate, the temperature trend actually shifts at lower temperature. Mercuric glycolate has the lower solubility, most stable species, precipitating solid phase. However, at higher temperature, the stable precipitating solid phase will be mercurous glycolate. For format, mercuric format will always be having lower solubility compared to mercurous format. These are all important in order to devising recovery of mercury for separation purposes. So what we have done here, mercury shows really complex phenomena, including oxidation state, redox phenomena, and the different phase separations as a function of pH with volatility, different vapor pressure and solubility of different phases, and all have been different thermophysical phenomena are being well modeled using the MSE thermodynamic framework, which gives a good insights to devise separation processes to actually comply with regulatory and remediation standpoint. After mercury, Now I'm transitioning into the PFAS compounds. PFAS is the emerging contaminant, uh, which has severe ecological challenges. PFAS is a synthetic fluorinated compounds developed in 1930 and widely used for everyday use components such as non-stick cookware, firefighting foams, textile, packaging, thermal fluid, and industrial surfactant. The key of these PFAS, which are par and polyfluoroalkyl substances, is the bond between the carbon and fluorine. So the bond is so strong, it becomes indestructible, and it is persistent in the environment. So these compounds are also termed as forever chemicals. Due to their stability, they can accumulate and contaminate water, soil, air, and through that can bring in severe health concerns, which includes immune suppression, liver toxicity, and developmental impacts, and even cancer risk. Uh, uh, Mostly the persistence and mobility of these compounds is driven by these compounds can exist both air, soil, and the surface water, and could affect human, wildlife, even could be found in remote regions such as Arctic. Due to the ever presence of this compound, the EPA has finalized some enforcement. So in certain places, some of the PFAS compounds are not regulated to have more than parts per trillion in water. Given the persistence of this compound and complexities of this chemistry, advanced thermodynamics and transport property modeling can, can actually aid to devise remedial actions. What are the key here over here is the role of pH. Actually, role of pH divides the thermodynamic behavior of this PFAS, whether this PFAS stays in the aqueous phase as a neutral species or unequal, which drives the solubility of these compounds. More solubility of these PFAS compounds will actually rather make them harder to remove because it will accumulate in water at a greater concentrations. Also, vapor pressure and Henry's law constant, which are very important, which gives the partitioning of the compound and allows these compounds to be available into the air. Also, the effects of coexisting ion and the complexations are key because it can hinder the separation process, such as adsorption or the membrane-based separations. So the extensive study of thermophysical properties are essential for these PFAS compounds to actually come up with a good data, which will allow us to come up with the design for remedial action. And here, WELI's simulation platform could help us to sort or to critically evaluate experimental data and come up with a model which provide good starting point. One of the good news pertaining to PFAS compounds that there are already databases such as Interstate Technology and Regulatory Council, IRTC, EPS, Comptox, provide us as a starting point. A lot of data has been compiled from thermophysical properties, including solubility, VLE, and critical micelle concentrations. However, there are significant inconsistencies resides within the available experimental data. As you can see for certain compounds, like I showed the partial process of this TFA compound, trifluoroacetic acid. The partial pressures actually reported from different sources vary by an order of magnitude based upon their assumed complexation constants, whether they are more soluble or not. Also, the vapor pressure, a solid, liquid, or for perfluorooctanoic acid also shows order of magnitude difference where data are available from the different sources. And so does the pKa's of these compounds. At 25 degrees Celsius, it shows a large scatter. So identification of which set of data to choose in order to develop a trustworthy model is of utmost importance. And we actually do utilize different sources of data to come up with a model. For example, between Bowden and Kasuna and Hori, we take call which data to use in order to parameterize our model. So these are some modeling results I am going to show for one of the representative PFA compounds, trifluoroacetic acid. For example, here I show the vapor pressure of this compound. Experimental data for this case are all in agreement and available from different sources over a wide temperature range from -10 to 210 degree. And actually, vapor pressures of these TFA compounds is being well represented using the MSE framework. Then the partial pressures of trifluoroacetic acid. As I mentioned, compared to Bowen, we chose Kasuna and Hori because there are other literature that validated this data. Although we didn't produce very good representation of the experimental data, it's only qualitative and shows the correct trend with the changes temperature from 5 to 25 degrees Celsius. Alongside this partial pressure, we also model the dissociation constants for trifluoroacetic acid. The dissociation constant in this case is available from one source and only limited to 25 degrees Celsius from Milne and Parker. However, the temperature trend of this dissociation constant of this TFA, which breaks down into C2F3O2 minus and hydronium ion, is of importance. So we have actually captured the trend of dissociation constant from trichloroacetic acid and used it to extrapolate for trifluoroacetic acid. And at the end, this is the VLE diagram for TFA and water system at a constant pressure of 1 atmosphere. What we can show here, the azeotropic nature of this VLE is well captured. So did we capture the pure vapor pressure of these compounds. With that, what we have shown that reliable thermodynamic modeling could be done with utilization of the correct data, which gives us good predictive ability in terms of thermophysical properties of perfluoroalkyl alkane compounds, which actually very important as an input for design remedial actions. So significant variability does exist within the literature for vapor pressure, pK, and CMC. And here thermodynamic tools such as OLI's MSE model could come as an aid to validate available experimental data, where we have created the model based upon the best available experimental data. And with that, I would like to conclude with saying throughout this talk, I have presented the MSE thermodynamic framework for predicting contamination or thermodynamic property of contaminants, wide ranges from heavy metals to the emerging contaminant such as PFAS. MSE model in turn provides a robust framework for speciation, solubility, and phase equilibria calculation, which in turns at the beginning, as I said, allow us to devise or see how the chemical compounds dissolve, react, and translate or transform into other compounds. Coupling with the experimental data with this predictive modeling enables us to better risk assessment and devise sustainable remediation strategies. With that, I would like to conclude today's talk, and I would also acknowledge my colleagues, Andre Andarko and Ahmed Mohammed from OLI Systems for their valuable inputs into my today's talk. Thank you.
Thank you so much, Gaurav. So it's a little bit hard to show our appreciation on this platform, but folks, feel free to add your appreciation in the chat window with a comment or a clap if you can find the emoji you want. And I want to thank Gaurav for that incredibly informative and well-organized presentation with great examples, fabulous insights into the capabilities of the simulation software. And a reminder to or a few more reminders to our participants that OLI Systems is willing to share the slides that they've presented today. So we will be sending those out to everyone who's registered shortly following the seminar. And we will also be posting the recording to the AWSP YouTube channel. So you will have access to these materials. If you have a question or a comment, please go ahead and add it in the Q&A panel, which you can access on the bottom of the Zoom window. And I will start off with a question. So back to the middle example about mercury, you provided some nice examples of how the speciation and solubility depends a lot on complexation with organic compounds, and you gave some examples with some fairly simple, easy to characterize compounds, oxalate, formate, etc. And I'm aware that a lot of mercury contamination issues in natural systems, would involve complexation with natural organic matter and different types of natural organic matter, humic acids, et cetera, which of course are a lot more difficult to characterize. So I'm just curious if you could provide any insight into how you would handle that in the modeling and software, and to what extent how do you handle modeling more complexation with more complex organic compounds, and is that a limitation, et cetera? Are there data gaps?
Yeah, first of all, thanks, Kara, for giving me this opportunity for presenting in this platform. And this is a great question. To add to this point, we actually modeled humic acid. Although I'm not presenting over here, but we have modeled for humic acid, and we have characterized humic acid based upon its molecular weight. And we have a modeling with humic acid in the presence of mercury, or it could be enhanced like as we get more data on those systems. So today, if someone has access to our software or have a collaboration with us, actually, we could actually run some simulations using complex components such as humic acid and mercury, and see their speciation, how those things derive solubility of certain mercury species. And we could do a lot more based upon their thermodynamic properties.
Wonderful. That's sort of what I suspected. So while others are formulating their questions, I'll go ahead and ask you another one that I have on my question list. Back to your first example on the rare earth elements, I'm curious if you have had any opportunities yet to work on projects or work with researchers who are interested in recovery of rare earth elements from different waste streams.
Yes, we are actually working with researchers from different national labs for the recovery of rare earth elements from different sources like coal ash sources. So we have worked on that, and we have a book chapter on that. We did a lot of work initially for the recovery of rare earth from phosphogypsum waste, using not only inorganic acid, just such as sulfuric acid and phosphoric acid, also organic acid, which are environmentally benign. We did also work on recovery of rare earth element from modern day electronic scrap, hard disk devices, using a novel electrochemical separation process driven by sulfuric acid and hydrochloric acid and sulfuric acid, where sodium sulfate has been utilized to separate this rare earth in the form of mixed salt. So in the nutshell, we did a lot of work on the separation and recovery of rare earth element from complex fish stream.
Great, those
And
are great examples. I think that's a research area that a lot of our members are quite interested in. Let me ask a question that's more general that might be of interest to some of our academic participants. For a researcher at a university to collaborate with you, do we have to have funding already? Like, are there any internal resources at OLI Systems that are available to at least like initiate a project? I imagine, collaboration could be around either identifying, better parameters or, parameters for a system that isn't fully developed yet, or addressing some of these discrepancies that you pointed out, or it could be an application. How does that type of collaboration usually get started?
yeah, we are open to collaborate with any kind of research opportunities. Like where the new areas may be emerging, right? PFAS and toxic contaminant. There are a lot of interest in this area, but there are limited data. So in that case, we can do initial modeling and give them the initial operating window, where can they do separation experiment or even obtain fundamental data. Then we can take the data and hone our model to generate next set of predictions. We do collaborate a lot with people who are interested in separations. For example, I gave rare earth separations. We are working with people who are actually separating the value metals, uh, cadmium, tellurium, from the solar cell. Who wants to garner more insights? Which chemistry do we use? What will be the best operating window to separate out certain compounds? And in that sense, based upon literature data, we can actually devise or develop our initial model, which could guide them to develop those kind of separation processes. So in general, we are open for all kinds of collaborations with academic. We have resources. And not only we could utilize the data, we can go for funding in new areas.
That's
And
great to hear. We have a question from one of our participants, Ibrahim, who thanks you for your insightful presentation. And he is a water researcher in Nigeria who is working on his master's degree in Algeria as an African Union scholar. And he's curious to know if OLI Systems has any ongoing or planned projects with collaborators on the African continent.
Yeah, I can take that. Yes, OLI does have a global team. So we have a EMEA team, Europe, Middle East, and Africa-based team. Currently, that team is headquartered in the UK, but we do have clients in Africa. We can certainly engage with you, and we'll be happy to have a conversation to see if there's an opportunity. But yes, we do. We have customers in about 35 to 40 different countries around the world, and we do have subsidiaries in some parts of the world. And we're rapidly continuing to expand that global engagement as well.
Good to hear. All right. Well, with that, I would like to bring our webinar to a close. I want to thank our speakers one more time for this extremely informative and interesting seminar. I want to thank Erica Marone at Stone Harbor Systems for her excellent support on the organization and logistics and helping everything to run so smoothly. I'd like to thank all of our attendees for joining us today. And also, we have another upcoming sustaining member webinar. It will be by Dynamita Systems on Tuesday, November 4th. So we will be sharing more details about the content and how to register soon via our email listserv and our LinkedIn. Thank you, everyone.
Thank you.
Thank you.